Okay, it's been brought to my attention that some of you are having some difficulties with translating from your understanding of whole shell or Bohr model of the electron configuration into subshell. So I thought I would make a short video to help bridge that gap in understanding, and please always reach out for questions and help as you need be. So let's start off by looking at the Bohr model that we have previously. So the Bohr model has our 2n squared rule. So we've got our first shell, second shell, so n is the number of shells. So n is the shell number. And 2n squared is equal to the maximum number of electrons that can fit into a given shell. Noting that we have this other rule that also no more than 8 can fit into the last or the valence shell. So let's take the example of calcium. Calcium has 20 electrons. Okay, so if we're looking at the full shell model, we would go 2 in the first, 8, 8, 2. We would think that we might fit 10 into the third shell, but again, following that second rule, we can't fit more than 8 into the last shell. So we start to fill the fourth shell, and then once we go beyond 20, we backfill this shell here. So let's try and link this example with subshells. So our subshells, we've got, if we think about the subshell model of this, it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? So the geometry in which we're following is, just to put this to the side, is that each shell we are progressively filling in this order, and the 4s fills before the 3d, right? So that's the pattern, but let's now bring it back to linking with how this makes sense with our full shell. So let's join that up. So 1s2, first shell, so this first number is called the principal quantum number. Fancy way of saying the major energy level or the shell number. The letter signifies the subshell. And so remember, we've got our 4 different types of subshells. We're not really going to even go into F. So let's just look at the main ones in which we use. S, P, and D. The last bit of information that we get that's in superscript here refers to the number of electrons in that given subshell. So coming back to this subshells, in an S subshell we have 1 orbital. In a P we have 3 orbitals. In a D we have 5 orbitals. And an orbital is a region of space which electrons occupy. So if we go back to this idea of what's called the Pauli exclusion principle, or the Pauli principle, means that in an orbital we can have no more than 2 electrons. Right, so that means 0, 1, or 2 in any given orbital. So the maximum number of electrons we can fit in an S is 2. Because there are 3 orbitals, and in each one I can fit a maximum of 2, the max number of electrons therefore is 6. And in a D we have 5, and in each one we can fit up to 2, so therefore the maximum number of electrons in a d orbital is 10. Let's see if we can visualize this a little bit more as to why, following this geometry, as to why the 4s fills before the 3d. Okay, so let's look at our different shell or energy level. So if we say energy, and we're looking at subshell, first shell we only fit 1, so the 1s sits about here. So let's now look at 2, 2s, 2p. Then we jump to 3, 3s, 3p, 3d. Then we jump to 4, 4s, 4p, 4d, 4f. And what I want you to notice is we can see that there is overlap and that the 4s is actually at a slightly lower energy level than the 3d. So there's that overlap there. So I hope that starts to make a little bit more sense about how we go from full shell to subshell to orbital and filling the electrons therein.